Hello and welcome back to Digital ASIC Design. This module is about timing design in digital systems. It's a very important module in this course because a lot of design and a lot of the logic synthesis process is driven by the desire to manage the timing of the design and to meet particularly required clock periods. So in this module, we're going to be dealing with a number of issues related to timing design in the details in the digital system. First, talk generally about synchronous clock logic, what that means and what the constraints are that come from that. Then talk a little bit about timing issues in CMOS circuits. Talk about timing in the general flow in the CAD tool, leaving specifics for the synthesis process to a later module. Then finally, talk about techniques to improve performance, particularly concepts such as microparallelism that allow you to improve a clock period and overall performance essentially for free. This also allows me to introduce what I like to refer to as the course mantras. Mantras are, of course, a term used in religions for things you say over and over again because they're true. Well, these are the truisms for this course, and you'll be tired of these mantras by the end of this course. These are the four mantras: one clock, one edge, flip-flops only. Design before coding. Behavior implies function, and clearly separate control and data path. This module addresses the first mantra: one clock, one edge, flip-flops only. Here are the detailed specific objectives to this module in terms of the outcomes I want to achieve related to understanding how clocks are distributed, how they are used, how timing is calculated, and how this is done practically in a design in the CAD flow. Now, getting into it, leading into more detailed motivation of why we're doing this section. You're most probably familiar with the concept of synchronized design. This is a cornerstone, a critical aspect of most modern digital designs. Yes, there is the concept of asynchronous design out there, but it's rarely used today, largely because the CAD tools don't support it well. The central concept in synchronous design is a master clock is distributed to everywhere at the same time, and events are synchronized by this master clock using flip-flops and latches. More specifically, items are stored on those flip-flops and latches that are needed in the next clock period of the operation of the chip. Now, the logic design, the combinational logic between those flip-flops and latches, is what determines the clock frequency and thus the overall performance. Later, I'll show you how you can manipulate synthesis to actually get the clock frequency down. However, this is not a magic bullet. It can only do it to within the degree permitted by the designer. The structure of the design largely determines the clock period, not the proficiency of the synthesis tool. In addition, much of the CAD flow is related to managing timing, usually to achieve a specific clock frequency. These are often referred to as setup requirements. And you have to learn how to manipulate the CAD tools to meet setup requirements. In addition, you have to meet what we'll describe as hold requirements. We'll come back to this in the next submodule. But here, later in this module, you'll see why I recommend flip-flops only, because it's very hard to meet hold requirements with latches. Here are the references for this particular module. So here's a detailed outline of what we're going to do, starting with explaining the mantra, then getting into timing concepts, flip-flop and latch-based designs, how delay is calculated in CMOS, and how to manage, finishing up with how to manage multiple clock domains. This first submodule will cover these first four bullets here, the general concepts behind timing design. Okay, the first mantra. Say after me: one clock, one edge, flip-flops only. Say it again. I can't hear you. Seriously, why am I asking this? You will find your life with synthesis a lot easier if you follow this rule. I strongly recommend that at least for each module, you have one clock source and only use one edge of that clock. And for your entire design, only use edge-triggered flip-flops. Why? Because, particularly within a module, moving data between different clock domains, if you have two different clock frequencies within the same module, requires a lot of scripting in the synthesis flow. And requires careful thought about how you're going to do it, how you're going to manage it. So your life's a lot easier if you only move between different clock domains between modules. And towards the end of this module, I'll describe how to do that. If you need multiple clocks in your design, and frankly all designs do have multiple clocks today, it's a lot easier if they're related by powers of 2, but again I emphasize use one clock per module if at all possible. And what we'll do is we'll have resynchronizing flip-flops and FIFOs between clock domains if we need them. And we'll talk about that at the end of this module. So in the revision module, you saw diagrams like this. I just want to remind you about the general approach to timing design. Remember, the way in which logic works for edge-triggered flip-flops is on each positive edge of the flip-flop, the flip-flop outputs become equal to the flip-flop inputs simultaneously on all the registers in the design. Between the edges, the data propagates through the logic to work out what to present to the flip-flops at the start of the next clock cycle. And it does this simultaneously for all the combinational logic blocks in the design between the clock edges. And the key to good timing design is to make sure that that propagation through the combinational logic is completed before the next rising edge of the clock. And we'll show detailed calculations for that in the next submodule. This is how, in a digital design, the clock synchronizes logic events. By the way, how do you decide what has to go into the flip-flops? In essence, it's quite simple. What information has to be preserved between clock periods to achieve the operation that you want? So within each clock period, all the logic must propagate through a design, through the combinational logic, for all the possible logic paths in a design. And in a modern design, there might be billions of those. However, there's one path that is the slowest path. And it's this slowest path that actually determines the clock speed. And it's often referred to as the critical path. So in the example down here, I have multiple paths through this design. One of them goes through one XOR gate, or two of them precisely. However, another one goes through 3 adders in series. Which path is slower? Obviously the one that goes through 3 adders in series. That's a lot more than one logic gate. And in fact, you can actually calculate the length of the critical path in terms of the number of logic gates that it goes through from input to output. So you multiply the number of logic gates between the input and output of the adder by the number of adders, you'll actually get that logic depth here in terms of the number of gates. And in fact, experienced design teams talk about logic depth. And they talk about what logic depth they need to get close to, at least, in order to achieve the intended clock frequency. And in high-speed designs at gigahertz or so, you might even be talking about 10 logic gates in sequence. That is, you can only ripple through 10 logic gates in the 1 nanosecond between successive rising edges of the clock. So in addition to the logic and the flip-flops, we also have to distribute this clock that does this overall synchronization. Nominally, at least, the goal of the clock tree is for the clock to arrive at each and every flip-flop, that is, leaf nodes of the tree, simultaneously. The way this is done in practice is after placement, but before final routing, we run a tool that inserts a clock tree. And it looks something like the structure shown on the bottom right here. Here it's called an H tree because it basically consists of an H at each level of hierarchy. H here, an H here, that might not quite look like that, it is, and so on. The idea is that delay from the root of the tree to each and every possible leaf is made to be as exactly the same as each other as possible. The way to do that is to make these rounded lengths, length from there to there, as precisely matched to the length from there to there as we can, and so on for lower levels of the tree, and to make all the buffers, that buffer there and that buffer there, or that buffer there and that buffer there, as identical as possible in the design. And then the final runs to the flip-flops are made very short, so we get very low variation in clock arrival time amongst the flip-flops in those final runs. So by balancing this tree, we design it with the intent of achieving the goal that the clock arrives at all the leaf nodes at the same time. Now in practice, we can't actually achieve that. And there's two reasons why we can't actually achieve that. And that is process and temperature variations causing clock skew and noise causing clock jitter. Clock skew refers to systematic clock edge variation between different flip-flops. That is, the clock at one flip-flop will arrive at a different time than the clock at another flip-flop, and the worst case difference in this arrival time is referred to as the clock skew. Now on the previous page I said that the intent of the clock designer was to achieve a zero clock skew. So where does this come from? What it comes from are a process, voltage and temperature variations across the chip. That is, the delay of these two buffers might be different from each other due to a different process, i.e. manufacturing variations in the transistors across the chip, due to a voltage difference, VDD, a slight VDD difference between these two locations, and even due to a temperature gradient across the chip. These variations are in general not possible to predict in advance. In particular, the process variation, which is the biggest single cause of variation, is random. At its root, for those of you who are interested, it is because the number of dopant atoms that make an NFET an NFET and a PFET a PFET are only about a few hundred atoms per transistor. And you actually get a random variation in the number of dopant atoms per transistor because it's a thermal process used to put them there. Since you can't predict the number of dopant atoms per transistor, you can't accurately predict its delay, at least within a certain bound. So we don't know which clock will arrive first. We can't predict that a priori. Clock skew is the larger of the two here. However, you also get clock jitter. Clock jitter is the variation in time between arrival of successive clock edges at the same site. So at one particular location, the clocks will arrive at different times, mainly due to noise, particularly noise on the power and ground system, causing very slight changes in the delay of this buffer. This jitter, the variation in time at one and all particular locations, is generally much smaller than clock skew. In the equations I have here below, I haven't broken out jitter separately because it is smaller. I've really just lumped jitter and skew into a single skew number. And in Synopsys Design Compiler, they actually lump skew and jitter into one number, which is called the clock uncertainty. And we'll talk about this in the next Verilog 1 set of notes, where we go over the entire synthesis and design approach. So some comments on clock skew, because a lot of people get a little confused about this. Right? what happens is the semi-automatic, largely automatic clock tree synthesis tools try to get as close to zero skew as possible. However, they do end up with some residual skew because it's not possible to exactly match the capacitances on the clock routes because you don't know what wires are going to be around it when you actually put the clock tree in. However, it does work to guarantee a skew target. So you specify a skew target, and the tool tries to achieve that skew target. If you need to relax it, then you reiterate on the process. And that's what happens in automatic when you use clock tree synthesis tools. Now, at higher clock speeds and in more sophisticated designs, you can actually create more customized clock distribution. And you can add features such as having different skews, for example, having local clock skews different than global clock skew, even putting in a systematic skew. These features are starting to creep into automatic synthesis tools. However, we're not going to use such features in this class. We're going to stick to what is the most widely used approach, and that is one global clock skew target. So these are not assumed for this class. So that brings us to the end of this first submodule. Again, I remind you of a few key points. The critical path is the slowest path in the design, the longest chain of logic gates between flip-flop output and flip-flop input. This path determines the clock period and is largely determined by the designer when he or she does the design. The clock skew between any two flip-flops as the clock arrival time to any two flip-flops is designed to be zero, but is not zero due to a random variation. But it is bounded by a maximum skew that can be achieved by the tools. And finally, going back to the mantra, by far the easiest way to integrate clocks into your design is to use one clock and one edge of that clock within each module, and to use flip-flops only. I ask you now, please, to complete the quiz for this particular submodule before proceeding to the next submodule. Thank you very much.